All right, for the next 7 days you guys are with me, we're going to be talking about forces in motion, so let's jump right in. The first thing that we are going to talk about is motion. Motion is a change in position of an object over a time, and we have to have a reference direction such as north, south, east, west, up, down, left, right. Any of those things can help us describe motion. So how do we know that something has moved? In order to know something has moved, we need to use a reference point. And you guys use reference points all the time without even knowing it. When you're giving someone directions, you are using reference points. So a really easy example is this tree here. We could say, you know an object is moving if it moves past the tree. So a reference point is going to be something that is stationary or not moving. So let's look at a couple examples. So our first example we have with football. So football is like really easy because they talk about reference points the entire time. They talk about, kicking off, and they kicked off and they ran it back to the 30-yard line. Well, the 30-yard line is unmoving. It's at the same place the entire time. So that 30-yard line would be a reference point, as is every single yard after that they have marked with a dash. And the long lines that go across the field, 30 yards, 40 yards, 50 yards. Okay, and so those are all reference points to show that the players have moved the ball up or down the field. So let me show you a couple other examples. A reference point is a thing that is unmoving that you use to compare movement. So if we look at Barry here, it says Barry begins on the left side of the sink, which is the reference point. So our sink is our reference point. If we look at the middle slide, we know that Barry has moved. Even though we don't see him moving, his position has changed, and so we know motion has occurred because it says Barry has begun moving, but the sink stays in the same place. So we know he moved because now he's at the right of the sink, when in the first slide he was at the left of the sink. So if we look at the last one, it says Barry has made it across the room, and you can tell because there are reference points that stay in the same place that don't move. So now he is past the sink, past the toilet, past the bathtub, and he is all the way on the right-hand side of the room. Without those stationary objects, we would not be able to describe where Barry is in the room or to even tell if he has moved at all. Those reference points tell us, yes, Barry has definitely moved. Okay, let's look at another example. In this example, the reference point is the tree, and so we need to see if the car is moving. So in figure 1, our car is to the right of the tree, and in figure 2, we can tell that motion has occurred because now the car is to the left of the tree, showing that the car moved from the right to the left of the tree and motion has occurred. Okay? So that's a reference point. A reference point is a stationary object that you use to compare to see if motion has occurred. All right, moving on. And the next thing we're going to talk about is speed versus velocity. So this is something that you're familiar with. Speed is how fast you're traveling. So if you look at the first car, it said speed is simply how fast you're traveling. This car is traveling a speed of 20 miles per hour. Or he was walking 1 mile per hour. Or she was running 15 miles per hour. Those are all speeds. As soon as you add a direction to your speed, you turn it into a velocity. So velocity is speed in a given direction. So if we add a direction, so this car is traveling a velocity of 20 miles per hour east, now it's a velocity. So you could say it doesn't have to be the cardinal directions. It doesn't have to be north, south, east, west. You could say up or down or forwards or backwards, left, right. As long as you add a direction to the speed, you have changed it into a velocity. Okay, so super easy for speed and velocity. Also, what you need to know is how to calculate speed, which is speed equals distance divided by time. Same for velocity. Velocity equals distance divided by time in a direction. So you have to add the direction to it, and it kind of got cut off there, but I just put a little d. So velocity is distance divided by time in a given direction. Speed is distance divided by time. Okay? The next thing that we are going to talk about is acceleration. Acceleration is any change in velocity. It could be, get my pen going, speeding up, slowing down, or a change in direction. All of those things indicate acceleration. Okay, so we're going to go check out a animation on acceleration. Okay, so if we look at these three cars and we're talking about acceleration, two of the cars are accelerating and one of the cars is staying at a constant speed. So a constant speed means that each second that the car is moving the same velocity or the same speed. So if we look at the green car, we can see that each little time it moves, it's moving the same distance. So green car is at a constant speed. Both the red and the blue cars are moving with acceleration. So the red car is going to start out much faster and then it kind of slows down, where the blue car accelerates the entire time. So both red and blue are accelerating because you can see the blue car is going to finish first. So that's acceleration. You can see that I said changing direction, speeding up or slowing down would indicate acceleration. So moving on to forces, a force is any push or pull on an object that causes change in motion. Okay, so you can apply a force to something and it doesn't move, and so that would be called a balance force, which we're going to talk about in a second, but you're going to cause a change in motion. So a force is a push or pull that causes a change in motion, and here are some examples. Obviously gravity, which is a force between objects. On Earth, our gravity is pulling down on objects towards the center of the Earth at a rate of 9.8 meters per second. Okay? Electricity is the force of electrons. Friction, we're going to be talking about, is a force that opposes motion or a force between two objects that are touching. And then magnetism is the force of a field, and you guys are familiar with magnets. Okay, so let's talk about friction. So friction is a force that opposes motion between two surfaces that are in contact. The amount of friction depends on factors such as roughness of the surfaces and the force pushing the surfaces together. So even if you have a smooth surface, if the force pushing the two surfaces are together, you're going to create more friction. So the rougher surfaces, the higher the friction, the smoother the surfaces, the lower the friction. We're going to go check out an animation that shows you how that works. Okay. So we have this dude, and he's going to be pushing on this box, and over here we can change the amount of friction. We're going to put none on it first, and then, I don't know, we'll make this guy over here sit on top of the box. Okay, so we're going to apply a force to the guy. I guess he's going to hold the box now. So we're going to apply this force. We're going to apply a bigger force to get him to move. He's pushing him, and there's no friction, so the box is going to keep moving and moving and moving and moving because there's no friction. Okay? We're going to reset it. We know on Earth that that's not the case, that we have friction on Earth, so we're going to change it from none to lots. We'll put the guy back up on the box. We're going to apply a force to the guy, and we're going to make sure our applied force is bigger than our friction force so that we can get him moving. All right. Okay. And so once he does start moving, once we're applying the force and the guy is going, once I let go and he stops applying the force, the guy is going to slow down and stop pretty quickly because the amount of friction that is causing him to slow down and stop, which is why when you kick a ball through the grass, it's eventually going to slow down and stop. Okay, so that's friction. So now we get into, now that we know what forces are, like friction, like electricity and gravity and magnetism, all those forces, we need to talk about what a balanced force is versus an unbalanced force. So a balanced force is when the net force is equal to 0. Okay? Forces can be balanced when they're at rest or moving at a constant rate. Balanced forces are equal forces acting on an object in opposite directions, and they do not change the object's motion. So if you look at this picture right here that I just colored over, you can see that both of those people are pushing on that box, but because they are pushing on that box equally, the box doesn't move, so then you say you have balanced forces. Over here, you have a 200 Newton cat pushing down on the left, and a 200 Newton cat pushing down on the right, and so that is balanced. You have the same force pushing down on each side. And then the last thing is the orbit of our Earth. So our Earth is moving with a constant velocity around the sun, and it takes the same amount of time, 364 and 1/4 days, for every year to go around the sun one time. Okay, and so because that is moving at a constant velocity, it is a balanced force. It's not speeding up, it's not slowing down, it's not stopping. It is balanced. So things that are moving with a constant velocity or at rest are said to be balanced. Okay. So here are some graphs that represent balanced force. So we can see in our first two graphs that our object is moving. It is moving the same amount in every second. So here, it moves the same distance. So that is said to be going at a constant speed. So this object is moving away from its starting point. This one is moving back towards its starting point. Again, this is a constant speed. That straight line is going to indicate a constant speed, and we'll be talking about graphs more towards the end of this PowerPoint. The other one is this, which is an object at rest, meaning the distance stays exactly the same as time ticks on. Okay? Moving on to unbalanced forces. That is when the net force is greater than 0. So on your paper in your notes, I want you to write what the net force is for each of these things. So if we look at this one first, so this guy is pulling this way with 50 newtons, and this guy is pulling the opposite way with 30 newtons. So that means our net force, we are going to subtract opposite forces. We are at 20 newtons is our net force, which is greater than 0. So we have an unbalanced force happening. If we look at this seagull over here, it says we have an upward force, and I know it's hard to read, of 6 and a downward force of 10. So if we subtract opposite directions, 10 minus 6, our net force is 4 newtons. Okay? Over here, we have a leftward force of 10 newtons, and we have two rightward forces of 4 and 4. So 10 minus 4 plus 4 is 8. 10 minus 8, that is a net force of 2 newtons. And then last but not least, I can't see because I drew over it. We have an upward force of our rocket of 300 newtons, a downward force of 100 newtons, and we're going to subtract opposite forces. So 300 minus 100, we have a net force of 200 newtons. Okay, and we're going to go to another animation to check that out. Okay, so right here we have, I'm going to put the sum of forces on so you can see that and the values that each are pulling with, and we have a little tug-of-war game going on. So we're going to put this guy up here on the left. So we're saying right now we have a leftward force of 150 newtons, and then I'll put this little guy, he's only 100 newtons. I'll put this little guy up there. Okay, so even though we have this one dude and these two people on the right-hand side, you can see the leftward force is 150 newtons, and so is the rightward force of 150 newtons. So this should be a balanced force. So if we hit go, they're both pulling, and nothing is happening because they are both pulling with the same forces. So that object is not moving. That is a balanced force. So we're going to add another little guy on the left-hand side, and you can see now our leftward force is now 200, our rightward force is 150. So we have a net force, or sum of forces, of 50 newtons to the left. So when I hit go, the little cart of whatever that is, candy, should start moving to the left. And it does. Okay? So we'll pause that. So an unbalanced force is when you have a net force greater than 0. So in that case, we had extra. So I'll give the red team a little bit more help here, and we'll see what happens. So now we have a rightward force of 100 newtons, so we should see the candy start coming back towards the red side. And there it goes. The red team will, if I let it go, will win, and they get the candy. Okay, so an unbalanced force is a net force greater than 0. And this is what the graphs look like for an unbalanced force. If you see a curve in a distance time graph, that is going to represent acceleration, and acceleration means unbalanced. It's speeding up, it's slowing down, or it's changing direction. That curve indicates an unbalanced force. So now that we know all about balanced and unbalanced forces, we're going to get into Newton's laws of motion, which you may or may not be familiar with. But the first one is objects at rest will stay at rest. Objects in motion will stay in motion at a constant velocity, meaning same speed and direction. We learned about that already. Unless they are acted on by an unbalanced force. So our little owl guy over here says objects keep on doing what they're doing. If they're at rest, they're going to stay at rest. If they're in motion, going a constant velocity, they're going to keep doing that. Just like the Earth goes around the sun at a constant velocity, it just keeps doing it and doing it and doing it. It has been doing it for millions of years. Okay, so that's Newton's first law. It's also called the law of inertia. Okay, so next we are going to watch a little YouTube video to talk about inertia. Again, inertia is the tendency of objects to resist change. Just like Garfield, he's laying there. He doesn't want to get up. He's going to keep on doing what he's doing. But let's watch this Steve Spangler experiment on inertia and eggs. Okay, so what they have set up here is they have the pie pan, and they have the little toilet paper roll with the egg sitting on top. And they're going to hit the pie pan out of the way and hope that the egg is going to drop straight down into the cup. So if it does, it's because that egg is going to want to keep sitting there, not moving, and so it's said to have inertia. So the egg is going to want to stay right where it is without moving, because they're not going to touch the egg, and the egg should drop straight down. So let's see what happens.
Yeah, don't knock over the glass, but you're going to give it a little pop. Ready? Here we go. 3, 2, 1, give it a pop. Oh! Nice. That was good. See?
Thank you very much.
When we instant replay, you're going to that was you got luck.
That was good.
That was luck on this one.
That was
good.
luck.
That was good. That was
much better
that
than
was
this.
skill. No, that was fine. So I was thinking if 1 is good, I've never done 5 before.
Well.
So I'll let it play through, but they're going to set up the experiment for 5 eggs, and I'll let you watch it one more time.
Over here and enjoy.
Okay, so he's got the 5 set up this time.
Just pop it out of the way and see if we can get them in. Ready?
Okay,
5 in. Here we go.
All right.
3, 2, 1.
Oh!
Look at that, people. That's 5.
Man.
Is that awesome?
That is phenomenal.
Okay, so you saw the egg, it sat there forever and ever, and then they moved the underneath, and then it moved downward. But because it had inertia, the egg didn't move, and it dropped straight down into the cup. So this is going to show 2 examples of inertia happening. So first is the golf ball sitting on the tee. It's going to sit there forever and ever and ever unless some unbalanced force like the wind or the putter acts upon it. Okay, so that's the first one. And then the second one is once the putter hits it, it should stay in motion forever and ever and ever unless an outside force acts on it like gravity and air friction and the friction of the ball touching the grass. So those are 2 examples of how objects in motion stay in motion. Okay, if you look at this next example, you can see if you're in a moving car that's going 50 miles per hour, you are also moving 50 miles per hour. Even though it feels like you're just sitting still in the car, if you're inside the car and the car's going 50 miles per hour, so are you. So if you're not wearing your seatbelt, what's going to happen is if you get in an accident, you are going to continue moving forward at 50 miles per hour because there's nothing to stop you, only that brick wall is stopping the car. Which is why when you hear about car accidents, you'll hear about people being thrown from their vehicle and being really far away from their vehicle because they weren't wearing a seatbelt, because this is exactly what happens. Okay, so moving on to Newton's second law. Newton's second law describes the relationship between gravity, mass, and distance. So the formula is force equals mass times acceleration. So the first thing we're going to talk about is if our mass is different, acceleration due to gravity is exactly the same, what is going to happen? And so what a lot of you think is that when you drop 2 objects, that the heavier object will hit the ground first, which is totally untrue. When you drop 2 objects, they will hit the ground at the exact same time. What is different is the amount of force that they hit with. So what I'm going to show you is a hammer feather drop. that they did on the moon, because there's no air on the moon, there's no atmosphere, so there's no air resistance. So I'm going to show you that so you can see, and I want you to watch carefully, that the feather and the hammer are going to hit the ground at the exact same time. What's different is that the force that they hit with, because the hammer has a bigger mass, the force is going to be much bigger that the hammer hits with. Okay? So let's get this going.
Let's suppose that you're writing a really important email to a colleague.
A feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
Okay, so it's kind of hard to see on here, but you can go look that up and watch it 50 times and see that both the feather and the hammer are going to hit the ground at the same time. Okay, so here's another example. If you throw a tennis ball and a bowling ball with the same force, which will go further. So I'm going to show it to you in terms of math so that you can see what that looks like. So our force of our throw is going to be 20 newtons. Newtons is the what force is measured in, okay? So the force of our throw on both the tennis ball and the bowling ball is going to be 20 newtons. We're throwing them with the same force. The mass of the tennis ball is 1 kilogram, while the bowling ball is 5 kilograms. So we can see our mass of our bowling ball is much higher. So if we set up our F equals m times a, acceleration is exactly the same, or is going to be different because the mass is different. So our force here is 20 newtons equals 1 for our mass times acceleration. We don't know. So if we figure that out, if we do, if we want to get a by itself, we divide by 1 on both sides, 20 over 1. Our acceleration of our tennis ball is going to be 20 meters per second. If we do the same thing with our bowling ball, if we want to get, we have 20 newtons, which is our force, set up, equals our mass, which is 5, and acceleration we don't know. We divide by 5 to get acceleration by itself, and we end up right here with 4 meters per second. Okay, so what that means is that down here, the faster the acceleration, the further the object will travel. So our tennis ball is 20 meters per second, bowling ball 40 meters per second. So our tennis ball is going to travel much further than the bowling ball. Well, duh, we could have figured that out without doing the math. I just wanted to show you the math behind it and show you how to use that formula, force equals mass times acceleration. So if you take a heavy object and a light object and you apply the same force to them, the lighter object is going to go much further because it has a lower mass. Okay? If we want them to go the same distance, then we would need to increase the force that we throw the bowling ball with, or decrease the force we throw the tennis ball with to get them to go the same distance. Okay? And last but not least, we have Newton's third law of motion, which is for every action, there's an equal and opposite reaction. So if we look at our first example, we see that the ball is coming in at an angle, and so when it hits, it is going to bounce off in the opposite angle and direction from what it came in as. If we look at these two people over here, they're on wheels, so we know if they push against each other going this way, then they are going to move backwards in the opposite direction. Okay? Let's look at some other examples of Newton's third law. When you sit in a chair, your body is going to exert a downward force on the chair, and the chair is going to exert an upward force on your body. The two forces resulting, the force on the chair and the force on your body, are called action and reaction forces. Okay? So the force downward is equal to the force upward, which means that's why you are not moving. Okay? So some other examples of Newton's third law of nature that you're familiar with. The first one is fish swimming in the water. So a fish is going to use its fins to push water backwards, which is the action. In turn, the reaction is that the fish goes forward. And you're familiar with this too. If you ever swim in the pool and you are pushing the water backwards, your body is moving forward. Same thing with a bird. The bird is going to push down on the air, and the air is going to lift the bird upward so that the bird can fly. Those are all examples of Newton's third law. Action, reaction, okay? For every action, there's an equal and opposite reaction. That is Newton's third law of motion. The last thing that we have to talk about are motion graphs, and we have been working with these all year long, so you should already be familiar. These are distance time graphs, or position time graph is the same exact thing as a distance time graph. So if we look at our examples, you need to know what is happening in a graph by its shape. So this first one is the object is moving at a constant speed away from start, and you're going to fill these in on your notes. In our second one, this object is accelerating. You can tell because there's a curve in the graph. This one, our object is at rest, and we've talked about these already earlier in our slides, so our distance is unchanging as time continues on. This one is a constant speed. It's a nice straight line. That straight line indicates a constant speed, and it's going back towards the start. We are accelerating back towards start. We started off slow, and then we got a steeper line, so that's faster. And then this one, our object is decelerating or slowing down. So we started fast with a steep line, and then our line got flatter back towards start. And then, of course, our object is at rest in this last one. Okay? So you may be familiar with slope, but slope talks about how fast something is. The steeper the slope, the faster the speed. So if we look at our first one compared to our second one, we can see that the slope is like this. So that is going to indicate something that is moving much faster than this flatter line over here. And this line, like this, would be an even faster speed. So the steeper the slope, the faster the speed. So fast, constant speed moving away from start. Slow, constant speed moving away from start, and then the same thing coming back to start. So fast, constant speed moving towards start, and again, I could even make that steeper, indicating that it would be even faster. This one's going to be slower, and I could even make the line a little bit flatter, indicating, as long as it's not a flat line, flat is going to mean at rest, but the flatter it is, the slower it's going, okay? So slope is going to indicate to us in a distance time graph or a position time graph how fast the object is moving. Okay, so I want you to use the following graph to match the letter to the correct statement. An object moving at a constant speed. Constant speed is going to be a straight line. Okay, this is a position time graph. Constant is a balanced force. It's a straight line. The only straight line is at letter B. It says this object accelerates quickly and finishes first. So we're looking for the one that finishes first. So if we look at time, this one is the least amount of time, so that one's going to be finishing first, so it has the quickest acceleration. So the second one is A, and it says this object accelerates slowly. You can see that this line is kind of flat, and then we get this curve in the line indicating acceleration, so that one is C. And the last thing we're going to talk about is graphing stories, which I know you guys got in your graphing unit, but we're going to talk about it. It says, remember a graph shape can tell us what happened. So we're going to talk about Darcy the dung beetle. It says, Darcy the dung beetle was a happy little bug. One day he decided to take a walk to the nearby dump. He left his home and crawled at a calm, constant pace. This means he went slowly, so we need a flat line. So look at the first part of this graph here. He sat down and remained there at the dump and enjoyed most of his meal for most of the afternoon. So he didn't move, so we have this next flat line here. After he was finished, he remembered an appointment with his friend. He quickly returned in the direction of his home, but passed his house and continued on till he reached his friend's house. So we need to have a steeper line going back to start, and we're actually going to go past start because it says he went past his house and continued. So you can see that this line here is our starting point, and he went past that, and our line is nice and steep, indicating that he continued on past his starting point. Okay, so that's what this graph would look like. You would have a slow, steady, then he went and rested, and then he went back past start towards his house. So we're going to be working on graphing stories in class too, and I know that we've already done this. It's just a review, but this is all part of the things that we need to be talking about with this unit. Okay, and that is going to be it for forces in motion. Please make sure that if you have any questions that you are talking to me in class so that we can go over anything that you have questions on. All right, see you in class.